All right, good evening. Welcome back. I'm happy to see still so many persons. Before we start, just a few administrative things. I said I would mention this today. So you're supposed to write some reports. The number is not fixed. It depends on the content. It depends on your academic age. At a certain point, you start, and I will tell you if you have to continue forever or if it is enough. The content, you can choose the content. Of course, it has to be related to this topic. You can either do one exercise, which is mentioned in the notes, or you can open a book, which is on the second website, and find something you find interesting, or you can work on an example. If you find an example of something closely related to what I said, you can try to understand this example and write a report. The only thing is it has to be with my notations, because if you use other notation, then nobody can use your report. So if the report is from a book which use slightly different notations, please try to transpose into the notation I have introduced. But the content is more or less free. If you are not sure, you can ask me. Of course, I expect something from you. You are free to use any help, but still it should be a work from you. If I see that you just copy and paste something from another source, I wouldn't be very happy. And there is a new rule this semester compared to a previous semester. I would like some regularity. It means I'm not happy if you give me 3 reports the last week of the semester. So please, and this will have a negative impact on your grade. So try to be regular, maybe 1 report every month. This is much better for you, and it's much better for me, and it's also much better for our teaching assistant. So please try to be regular. And finally, the grade. Don't be scared by the grade for 2 reasons. First, I'm not very strict. But secondly, if you're not happy with your final grade, you can still withdraw from this course at the last minute. And nobody would know. It would not impact your GPA. Why I do this? Because I prefer that you learn something instead of not learning it. So you can stay, and if at the end you don't submit any report or you don't want to get a grade, okay, you are just absent for this course. This doesn't apply for new pay student. So a new pay student, you have to withdraw before if you want to withdraw. This is a different rule. If you have any question, you can ask me now. Yeah. The length of the report, again, it depends on the content. If you write a 5 pages long report or a half-page report, it makes a difference. Up to you. It depends on the topic. Yes, you can write a report about anything related to this. And yes, how to submit? No, you submit it directly to me. Either a paper version you can give me during this class, or you send me an email with an electronic version. So both, but I don't use stacked. Yeah. Okay, so we can check together at the end. If you have a problem with finding the website or anything with the website, we can decide at the end. We can discuss at the end. Usually I start with a reminder. So remember, topological space is nothing but a set, and you choose a family of subsets. You decide what you call open subset. And there are 3 conditions, and one is important. And somebody asked me why we consider only finite intersection. Think about the following thing. If you take balls centered at one point of decreasing radius, and you do this intersection, what are you going to get? Infinite number of balls. What are you going to get at the end? The intersection is just 1 point. And we don't want 1 point to be open. In the definition of open set, we don't want just 1 point to be open. That's why in the set of conditions, we consider only a finite intersection of open set is open. Okay. Now, once you have this, you have the notion of neighborhood of a point. Any open set which contains a point is a neighborhood. Hausdorff property is simply that whenever you have 2 points, you want to be able to separate them. So it's a condition which says that you have enough open subset. Now I also introduce the notion of basis, because you cannot describe all open set. You define what is a basis. It's a family of subsets that you can always put between 1 point and any neighborhood. And if you can find a countable basis, we just say that the space is second countable. I also introduce the notion of subspace topology. If you have a set with some open set, you can also restrict everything to another set. So you take intersections, so only the intersection of the white thing and the yellow one. And this is, you get what is called the subspace topology. Observe that the final set here doesn't look like an open set in the initial topology, but still you say that it's open with respect to the yellow part. I also just mentioned connected and compact. Connected is easy. Compact, it's a very fundamental notion, but it's not so easy. Topology is related to continuity. So I define what is a continuous function from one topological space to another one. It just, the preimage of any open set is an open set. And if you have a bijective map, which is continuous with the inverse also continuous, it's called a homeomorphism. And with this, we can define a manifold. So this is a manifold. What is it? It's precisely a topological space which has enough open set in order to separate points. It has a countable basis. And for any p, any point on this, there is a homeomorphism. So there is a bijective and bicontinuous map from a neighborhood of p with an open set in M, if it is of dimension M. Be careful, I update the notes. So if you download them on your computer, check that you have the most recent version, because I change when I find mistakes. And if you find mistakes, of course, you can also let me know. I will correct them. Okay. So remember, with topology, we define the root at the beginning. We decide this is an open set. This is important. And then, because a priori, you don't know what is an open set on this set, on this object. Okay. Right. So today we are going to study manifolds. Just a remark, it's not really important, so I will not spend too much time on this, but a topological manifold has two properties. You know, you can already see locally, it's not very different from a part of Rn. The problem is globally, it's different from Rn, but locally, you have small patches which look like Rn. So it turns out that topological manifolds are what we say are locally connected and locally compact. I told you, if you don't understand this sentence, it doesn't really matter, which means locally, it's always connected. And connected, remember, it means in one part. It's not separated into two parts. So locally, it's always in one part. You can always find a small, around each point, you can always find a neighborhood which is connected. And locally compact, it means it's the same. Locally, this can be a compact set, so you can find any covering has a finite subcovering. So it has good properties locally. And there is one more property, also topological manifold. They are always the union of a countable number of compact sets. So compact set you should, how to think about compact set, in fact. It's not exact, but you can think about it's more or less closed and bounded. So they are nice sets, like a square. So what is the meaning of this sentence? Is that a manifold is always a countable union of compact sets. So it's a countable union of nice sets. It can extend up to infinity, but a cauliflower, for example, is not a manifold because you would have to cover with an uncountable number. So countable means always you can count the first one, second one, third one, even if it goes up to infinity. But the big difference is with the real line. The real line, you cannot count the numbers on the real line. This is a remark about manifold. Everything is coming from the fact that locally it's essentially like Rm. There is a nice result for two-dimensional manifolds, which I want to mention. Two-dimensional manifolds are, in fact, quite simple about two-dimensional manifold. And there is an illustration in this. I put some illustrations in the lecture notes. This is a theorem. I didn't take the balloon again, but okay. This is a two-dimensional manifold. I think it's slightly better than this one. Essentially, they are all like this, plus some handles. So you can always attach some parts like this. And the statement says exactly this. Any two-dimensional manifold is a sphere plus some handles. So you can see a picture in the note. So the theorem, any compact, so it means it's in a ball, it's not going up to infinity, but on a ball, any compact two-dimensional. There is one more word, which is connected. This is connected. It's okay, we know, but orientable, which I haven't defined, and I will not define it right now. Orientable manifold. Is homeomorphic. So it means essentially you can deform it. Is homeomorphic to a sphere. To a sphere, yes. To a sphere with handles then attached to it. Like your favorite cup, there is essentially one ball, you have one sphere, and you have things like this which are attached to it. So all two-dimensional manifolds are of this type, or can be transformed, you can deform them into something of this type. Be careful if you represent them in 3 dimensions. You can have things quite complicated because one handle can go through another one and come back. So you can have something like this. I'm not sure. The picture in the notes is probably better. So they can interlace. They can, yeah. But still, this would be one ball with 2 handles. The fact that they interlace is because you try to see them in R3, but as 2-dimensional manifold, the fact that they interlace, the handles interlace doesn't matter. So look at the note. I'm not good at making pictures on the blackboard, so you can look at the notes. So this is a result for 2 dimensions. Be careful, there is nothing similar in 3 dimensions. It's much more complicated. But in 2 dimensions, that's it. And the number of handles is invariant if you deform continuously your object, you keep the number of handles. And this number of handles, the number of handles, has a name, is called the genus of the manifold of 2D, two-dimension manifold. This is just a name. All right. But yeah, representation in R3 can be misleading because this part can just interlace. Okay. Let's now come back to our manifold. And I take a point P. Remember, for any P, you can find a U and a part of Rm, which these two things are homeomorphic. So you have a bijective map, which is continuous and with inverse continuous. But it's like in reality, you can give coordinates. So if now on Rm, you put the usual grading, then you can say that this point has this coordinate and another point would have another coordinate, right? Like in reality, you have maps and the map is something in R2 usually, but the reality is on a manifold on Earth. So in fact, this is very natural. So let me just write a comment and write a name for this. So fix P belonging to a manifold, then we know then there exists U and phi. What is U and phi? U with U, an open set, a neighborhood. I can directly say it, a neighborhood of P. So an open set containing P and phi, it goes from U to Rm. It's this map, homeomorphic. Be careful, the image of U is phi of U, it is this set here. So it's homeomorphic, so it's bijective only between U and phi of U. You cannot say that it's homeomorphic between U and Rm, but phi of U, I can maybe write here, instead of directly Rm, you can write phi of U included in Rm. And then it's homeomorphic. Because you already know that any function is surjective on its image. So what you need to know is that it is injective. 2 points here are sent on 2 points here, 2 different points. Right. So we know this. It's a definition of a manifold. For any P, we have a neighborhood and a function which is a homomorphism between U and something in Rm. I'm consistent in the sense that if I call this a manifold M, the dimension is M. If I call it N, the dimension is going to be N, small n. But you know, this point here, this phi of P, it is in Rm, so it has M coordinates. I can write phi of P first coordinate, it's here, phi of P second coordinate up to phi of P M coordinate. And in fact, we will use another notation. Phi doesn't mean anything. We will write x1 of P, x2 of P. This is just a new notation, xm of P. And these x1 up to xm are called local coordinates of P. So you give one way to provide coordinates on this by using this homeomorphism between an open set here and an open set here. And you call this local coordinates. And still in the so the pair U phi is called a coordinate neighborhood. Oh, this is just a name. A coordinate neighborhood. Or simply, and I will probably use this word, a chart. Neighborhood or a chart. So it's really, you have a mountain and you have different maps of this. 1 second. And on one map, you have local coordinates for what happens here. Yes, you have a question.
RN, are they guaranteed that it is connected on this nice, like the drawing?
Okay, you know, I can shift this ball here, and I can manage to have it centered at, I can put the P here, because the translation would not change that it's a homeomorphism. So you can, I do it on purpose anywhere on Rm, but there will be a result which say, oh, you can always center it at 0 if you want. And you can even manage to have a, not only an open set, but to have a real ball here. There are such results, yes. So look, just remember a coordinate neighborhood or a chart, it's simply locally around a point P, you can give coordinates by using this phi. Right? Last time I said also I want to consider manifold with boundary. Because now these manifolds have no boundaries. Every point has a neighborhood which is like an open set here. But suppose you want a manifold which is, take this one and cut it somewhere. I cut it here. Now I cut my manifold here, and I just want to consider this part. It's going to have a boundary. So how can I define a manifold with a boundary? So I need to, and you have an example, a half space. If you take R here and R plus in this direction for starting at 0, this is a good example of a manifold with a boundary. This is going to be the boundary. And in fact, we will exactly use this. So we set Hn, it's a definition, and keep this in mind because this is exactly what I'm going to do. It's a set of points in Rn such that the last coordinate is bigger or equal to 0. So I take half of a space. Okay. What is a boundary of, I give a definition and a notation. This is for, it's a notation for boundary. If you have seen the partial derivative, this is the same curly D as partial derivative, but you can just think about a notation. The boundary of Hn, you can guess what it is. It's a set of x1, x2, xn minus 1, and the last coordinate is 0. So the boundary is just this set. Yes. So if you think, if this is a boundary, we have a half space, and we use this boundary. So the one of coordinate 0 in this direction gives you this wall. This is a boundary. So Hn is a half space, and its boundary is this. And now, this is inside R2. So we have the open sets, which are the usual one. But if I take an open set of R2, which is like this, I can take what we know now, the subspace topology. So it means I erase this. So this is exactly the subspace topology. You erase what is not inside the space. And I'm going to call this as well an open set. So we have in this picture, we have two types of open set. The one like this, and some which are like this. These are open sets. So we consider this set Hn with the subspace topology obtained from Rn, obtained from Rn. So we had the usual ball in Rn. Now I consider just this ball, but restricted to the space, the half space. And I will give a name to this. I give a name to this set and this topology. So we call, or we denote this topological space, because topological space with the same this is the same font as R, but we call it Hn. So it's really Rn that you have divided into two parts. You keep only the upper half, and you put the open set obtained by restriction. And this space, it's a topological space. We denote it by this letter. And now you can guess. I'm going to use this for defining a manifold with a boundary. So if this is a boundary, I will say this manifold, we have two types of open set in it. Either this one, which is going to be like an open set in Rm, as before, or a second type of open set, which looks like these ones. So now you have the definition of a top manifold with boundary. M-dimensional. In fact, I essentially copy the previous definition. M-dimensional manifold with boundary. So the difference is this with boundary is a topological space. It's a Hausdorff, mean it has sufficiently many open sets. It's a Hausdorff second countable. This is a basis which is countable. It's a Hausdorff second countable topological space. So exactly as before. Such, I give a name M and curly tau, curly T, such that any P inside M, any point, has a neighborhood and now we have two alternatives. Either in this situation or in this situation, has a neighborhood homeomorphic either to an open set of Rm, sorry, to an open set of Rm or an open set of HM with one more condition, is that this point P is on the boundary with P or phi of P, with phi of P belonging to the boundary of Hn. So you have two types of points, either one point which is inside or a point which is at the boundary and it's sent on the point of the boundary. Probably by mistake. The same dimension. The same M. So this is a manifold with boundary. And again, I put 2 or 3 examples in the notes. You just cut a usual manifold somewhere, and the intersection will be a manifold with boundary. So far, so good. But so far, we only dealt with continuity. Topology is about continuity. We would like to have to say that it's differentiable. We would like to have a smooth structure. We would like to take derivative on our manifolds. So we need to add a structure so that differentiability has a meaning. But how can I speak about, okay, let's forget the boundary for a second. Even how can I say that something is differentiable on this? Remember, it's the intrinsic picture means it's not inside a bigger space. I have defined everything without using a bigger space. So yeah, I'm cheating because I put this box inside R3, but it can be a 2-dimensional manifold, even if 3 dimension does not exist. So I need to speak about differentiability without having everything in R3. So this is a section 3, 1.3, smooth manifold. And it's a very nice idea. Smooth is the same if you have already heard about C infinity. C infinity, you know, you can differentiate as many times as you want. It's not only once differentiable, but you can take many derivatives up to infinity. So a smooth manifold is the same as a C infinity manifold. And I can directly give you the definition of a smooth manifold. A smooth manifold is, first, it's a topological manifold. Is a topological manifold. So it means it's something that we already know, but with an additional property. So it's a topological manifold, let's say of dimension M. Let's do a picture. What we know about topological manifolds? We know that whenever we take one point, we can associate a chart, and this is Rm, and we have phi. We know this. This is. Now suppose we have a second chart, which means I have a second chart on another copy of Rm. So this is phi, this is psi. We know that it exists for every point, there exists such a thing. So you take 2 different points and you have these 2 different pictures. But look, this composition, this is bijective. So I can also take its inverse. Phi is going in this direction, but I can also take a function from here to here, And if I do it, we have an intersection. If I manage to have an intersection, the intersection is, let's say, here. This is the image of this intersection here, and the image of this intersection is here. If it is in the intersection, it's in both sets. But look, I can take a function phi from here, or its phi inverse to here, and then this composition. And now we have a function from Rm to Rm. And no, you wait. And for function from Rm to Rm, we have this notion of differentiability. We know what is a function. It's calculus 2, but a function of m variables with value in Rm. So this is exactly the definition. So it's a topological manifold of dimension m together. So it's an additional structure together with a family of charts. And remember, a chart is exactly what I have represented. This is a set on a bijective map, a set on a bijective map. So a family of charts, and I will call it curly U, which contains a family of U. I call it, maybe I should have called this U1, phi 1, and U2, phi 2, just to be consistent. So it's a family of charts like this with phi alpha from U alpha to its image inside Rm. This one is phi 1 of U1. This one is phi 2 of U2. So it's a family of charts with 3 properties. So it's a family of charts, blah, 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 with such that the first property is, so we have a family of charts, so a local map. It's like in reality, if you want to cover a country, you have a family of maps, but you want to cover the entire country. You don't want to have one part of the country which has no map at all. So it's a family of charts such that the union, the notation is just ambiguous. This is a union over alpha of U alpha. Yeah, sorry, union. This is a union. You want this to be equal to M. You want to cover everything. Otherwise, you have a problem. Okay? Do it better. So we want to have enough map to cover the entire manifold. And the second condition is exactly what I mentioned on this picture. For any alpha and beta. So think about alpha is 1, beta is 2. I define the map or the function phi alpha minus 1 phi beta. It's exactly what I said. I take the reverse on its bijective. I can take it, and then the other one. So phi alpha minus 1 phi beta, where is it defined? It's defined on the image, exactly on this. It's defined from here to here. So it's defined from phi alpha of the intersection U alpha inter U beta. Take this intersection and send it here. And what is the image? It goes to phi beta of this intersection, U alpha intersection U beta. And the same, I can do the other one. This one, take the inverse and go here. So phi beta minus 1 phi alpha. This one is from phi beta of the intersection to phi alpha of the intersection. Now you have two functions, one from here to here and one from here to here, right? And you assume that, wait, I just finished 1 second. These two functions are differentiable, are smooth. So it means we have function from Rm to Rm, and we can differentiate them as many times as we want. Is there a mistake? Oh, yeah, you're right. I did a mistake. Sorry. Okay, sorry. So, yes, everything is not correct. So, thank you. Let's check. So I want to start. So phi beta minus. So the first one has an inverse. For sure, because you want to start here, and you take an inverse. So in fact, the first one is now this one. Here, here, and here. And so it starts from phi beta to phi alpha, and the second one from phi alpha to phi beta. Please check. Now it's, oh, no, not too many minus one. Okay. Yeah. Yeah. Yes, this is just your famous, your simple function from Rm to Rm. So you can ask that there's infinity.
But can I think of like C as R? It's like two real like for complex.
No, analytic manifolds are slightly different. So it's strong. It's a stronger condition if you assume that these functions are analytic. So it exists analytic manifolds, but here I'm dealing with smooth manifolds. But you have two functions from Rm to Rm, so you can think about a collection of m functions of m variables and assume that they are smooth. So we have the first condition, we cover everything. The second condition, it's a compatibility. It's also called the compatibility condition. And there is a third one, which I'm not going to spend too much time on. It is U is maximal. I've written the exact definition in the note. What does it mean? It means suppose you have one more, let's take one more chart like this, which satisfies these properties. So I take a third one which satisfies this, then automatically this chart is in my family. So I take the maximal family of compatible chart. I want to have all of them, not only a finite, I really want to have all of them. So there is this notion of maximal. It contains all charts which are compatible in this sense. And you can guess condition 1 and 2 have in fact a name. A family U satisfying 1 and 2 is called an atlas. And this is quite natural because you cover everything. And if you have the third condition, then it's called a maximal atlas. So a smooth manifold is a topological manifold together with a maximal atlas. You have a question? Yeah. Because if you don't impose 3 and you want to work with a new one, which is compatible, you are not sure that it is in the family. So in order to be consistent, you put it immediately in the family from the beginning. But there is a theorem which says if you have a family which satisfies 1 and 2, you can make it bigger so that you get a maximal atlas. So for any atlas, there exists a maximal one, and you consider this one.
As long as we have one, there should exist a maximum.
Yeah, this is correct, but you have to prove it. So whenever you have one, if we have, yeah. They always, it doesn't matter. Probably an atlas contains an infinite number of charts, but there still exists one which is the maximal one. So it contains everything. Now there is a nice thing which I will not develop any further, but take a ball. You can wonder, wait a second, you can wonder how many different atlas you can put on a ball, on a sphere, let's say on a sphere, Sn, a sphere S. You probably can think about the usual one that you obtain by taking it on a sphere, so you have also open set. But it turns out that on some sphere, depending on n, you have many different possible atlas which are not equivalent. I didn't define what is equivalent, but you can find information in the literature. So on some sphere, you have many different atlas which are not compatible. And I think it's even still an open question in some dimensions to know how many of them we have. I put a link in the notes. Yes?
What's the dimension and well, how is it the same?
Because you want to know why these two dimensions are the same. It is in the definition. In the definition, but you know, locally, you cannot have some, it has to be bijective. So if this part is bijective to Rm, it cannot be bijective to Rn and keep everything continuous. So this is not possible if n is different from m. No, but for two subsets, this subset has to be in bijection and homeomorphic to a certain Rm. You cannot expect that this is homomorphic to a different one. It is in the definition. Yes, one more question. These maps are differentiable. They are smooth. They are C-infinity. You know this? No, this is a definition. It's a definition. I call this a differentiable manifold is if whenever I have these two charts, there is a compatibility condition which is smooth. It doesn't, of course, at the end of the day, this you are going, on all pictures, you are going to see this as a nice, smooth manifold. But in fact, it's really in the way you describe this manifold that you have smoothness. Because the only smoothness you can get is on Rm. No, it's the composition. The composition, because what does it mean that it's smooth from this to this? It doesn't mean anything. So this has no differentiability structure for now. It's only when you compose everything that it is smooth. You can look at, this question. I put something in the notes, and I put some examples also in the notes. And you can study, this is an exercise, take some manifolds, for example, the torus. Take the torus in 2 dimensions. Study or check that it is indeed a 2-dimensional smooth manifold. Everything is written in the literature, but you can still learn something by trying to understand what is written. And you can write a report if you use the notations of this course. All right. So we know now what is a smooth manifold. This is the main condition, compatibility. And now let's move to something else. Take 2 manifolds, M and N. And I assume that both are smooth in the sense I have just introduced. what means a smooth map between them? What means that F is smooth between two manifolds? So we need a definition. And you can imagine, I'm going to go back to as part of Rn here. When I do this, it's always a certain Rm. And now I make a difference because this is manifold M with small m. And now here we have a Rn, which can be different because it's a manifold N. So the way I'm going to say that F is a smooth map is when I do this composition of these three things, it's going to be smooth. So definition. Let M and N be smooth manifolds. And F from a function which associates to any point of M, it associates a point, capital F, of this point. Okay, so it's a function from M to M. The map or the function, remember, map and function for me are the same. The map F is smooth. So this is a definition. If for any P inside M, I choose this P, there exists a neighborhood. And we know that there is a chart like this. So there exists this chart M, oh no, not M, sorry, U phi. This is U and this is phi. There exists another one, which is going to be V psi, a chart on M with T inside U, of course. But there also exists this N, this V psi, a chart on N. And now I need a few conditions with, I want to do the composition. So it means that the image of this set U has to be inside this one. So with F of U inside V, otherwise you cannot do the composition. So you need to go from something to something, the same, blah, blah, blah. So you need this compatibility condition. F of U is inside V. And then the composition. So you take phi minus 1, compose with F, compose with psi. This time it's correct. It goes from phi of U to psi of V. Yeah, it's inside phi of V. The image is slightly smaller, or maybe, yeah. But again, this one is in Rm. This one is in Rn. So you can speak about smoothness, even though it's not the same dimension. Then this composition, and I'm going to give a name to this thing here. I will call it F phi psi. I just give a name because it will be simpler. Then this composition is smooth. Again, I define smoothness without imposing anything on this object, but by local charts. Smooth, again, means infinity. And still in this definition, the set of all smooth F from M to N. So the set of all such functions is denoted by C infinity from M to N. This is a notation for all function f from M to N, so that when you look at local maps, it's smooth. Differential geometry, everything is local. You define everything locally. And a special case of this is the simplest manifold is a line R, right? So you can, this is a manifold. You can check it's a one-dimensional smooth manifold, the simplest one. So you can consider functions on M taking values on the line. You have a manifold and you associate a certain quantity to each point, the temperature at every point on Earth. This is a function from your manifold to R. And so if N is just R, we set, I don't want to set C infinity from M to R. We just write C infinity of M. When it's real value, we just use this notation. This is a special case where you could also have Rm or Rn. For example, if at every point you associate the direction of the wind. If on the planet you associate the direction of wind, this would be a function from your manifolds to R3 if you put at every point this. I'm not sure that it's smooth, but it's a different question. And let me come back to Rn, the general case. This is N. You know, I have considered from M to N, it can be that this function is bijective. So in the definition, if f from M to N is bijective, so it means each point is sent only on one point, and two different points are sent on two different points. So if f is bijective, and now we have two conditions, that f is C infinity from M to N. It doesn't imply that the inverse, now I can speak about the inverse. If it is bijective, I have an inverse. It doesn't mean it's also smooth. So I want to impose a second condition, and this and the inverse f minus 1, be careful, f minus 1 is from N to M. So if they are both smooth, we say that f is a diffeomorphism. Before it was a homeomorphism when we were just dealing with continuity. Then when we have differentiability, it's called a diffeomorphism. There is a word differentiable, diffeomorphism. This is just a name. But this is the best situation where your function is bijective and smooth in one direction with the inverse, which is smooth. Yes?
Can be an M-dimensional manifold or an N-dimensional?
Good question. If it is bijective, can we have them of different dimension? No. Automatically, I don't have to impose it, but automatically this can take place only if they are both of the same dimension. Yes. I can write it as a remark. There are diffeomorphisms only if they are of the same dimension. Diffeomorphism imply that M and N are of the same dimension, or small m is equal to small n. Okay, so look, I come back here to the situation where so this was a special case when it's bijective. I come back to the general case when we have m and n without the inverse. I'm not assuming that it's invertible anymore. But look, still in this situation, we had something like this. This composition, this function here, was from a part of Rm to a part of Rn. What can we define when we have a function from Rm to Rn? Calculus 2. Which is which matrix? The Jacobian matrix. Yes, my God. It's good to remember these things. You are second year, so you have learned this. First year, it's difficult. So when you have function of one variable, you can consider derivative. If now you have function of more than one variable, you can take derivative in all directions. And if you have n functions, you can take derivative of the n functions. So we can define the Jacobian. So of course, it's only defined locally. So when I write this expression, it means I need to be in the good setting where the image of U is inside V. It's implicit, otherwise it's not well defined. So since this F phi psi, which was defined from phi of U to psi of V, so I come back to the previous setting, with this inside Rm and this inside Rn is smooth. We can define the Jacobian matrix. I will record the definition. The Jacobian matrix at any point okay, I continue. I want to keep the picture for a second. At any point P inside U. So I'm going to define the Jacobian matrix associated to this point. So it's a definition. I will not write again all the setting because I introduced it in the note. It's written, but it's the same. We have two manifolds. We have a F going from this one to this one. We have a U with contains a point P, and here we have phi going in this direction, and we have a psi going in this direction. So in the previous setting, in the previous setting, in the note it's more precise, but in the previous setting, we set, I already defined it, but I recall, we set F phi psi as this composition of phi minus 1 F psi when it's well defined. And okay, There would be an ambiguity if I do this. So we define, in fact, we define what is important is the rank of the Jacobian matrix. We will see why. Because if I define the Jacobian matrix, it would be the Jacobian matrix associated with this point, phi of P, because it would be Jacobian matrix at one point for a function from here to here. What is really important is you have a matrix and you check the rank. So a matrix, what is the rank? You have some columns. The rank is how many of these columns are independent, or the same, how many of these rows are independent. So we set, and so the rank, this is a notation, rank of F at P. Probably I need more space than this. I define the rank of F at P. It is the rank of the following matrix. So I consider the, let me write it, it's type psi divided. If you think about it, you have not really too many choices for what you can define. Okay. So remember, this function is from a part of Rm to a part of Rn. So it means it has, the function has n components. The first one, the second one, the third one, up to the number n. And we have m variables, because on this space we have m variables. So I can take the derivative with respect to the first variable, second variable, third variable, until the last one. So it's a matrix with m columns and n rows. And it's a function from here to here. And if I want to associate it with the point P, I have to look at its evaluation at phi of P. So it's a big matrix. And I just take its rank. So I look at how many columns or how many rows are independent. And I call this the rank of F at P. Now you can complain. What is the problem with my definition? There is a problem with this definition. Now, look, here I indicate F and P, while here we have phi and psi. And remember, when you have an equality, you should have the same information on the left and on the right. So there seems to be a problem. But it turned out that the rank is independent of the chart. If you take a slightly different, this is an exercise, it's not easy, but it's take a slightly different chart and take a slightly different chart here, you will get the same number. The rank is the same. So it's, I write it as a remark. The rank is independent of the choice of charts. Precisely because when you change two charts, when you go from one to the other one, everything is smooth, so you don't lose anything. So this rank is independent of the choice of charts. And I mean by this, independent of phi and psi. However, it depends on P. If you take a different point P, it might be a different number. We will see an example. But yeah, whenever you have a function from Rm to Rn, you have, in fact, n functions, and you have m variables, so you can take the derivative with respect to the different variables. So it's independent of the chart, but it depends on P. Of course, the case of interest is usually when P is constant. Sorry, when it does not depend on P. So, but it depends on P in general. This number depends on P. Let me just add the case of interest. Of interest is when this rank is independent of P, which means constant on M. And I'm claiming that you have you're in calculus 2. Let me just mention this already now. We have seen this notion. So it's a remark. In calculus 2, we studied parametric curve. We studied parametric curves. But this, we are exactly dealing with this. Look, what is a parametric curve? Take an interval. I take an open interval. This is my manifold M. Take n is equal to Rn. This is my manifold N. What is a parametric curve? In calculus 2, I call it C, and it takes a T, goes to C of T. It's a description. It's this. Take an interval, and oh, okay, what is C of T? This is C of T. This is C of, let's say, 0. Then you move to C at time 1. Then you have a C at time 2, up to C at time 3. You describe a parametric curve. It's just you describe the motion of something in Rn. We have a manifold. We have Rn. This, so I can put it in color. This is our M. This is our N. And this C is now what I call F. And what is the Jacobian matrix in this case? We have only one variable. So the Jacobian matrix is a derivative, so it's a tangent vector. In this case, Jacobian matrix, it is equal to, usually we write it C dot T, which is d over dt of C at T, which is a vector. It's a tangent vector everywhere. And what is the rank of this matrix? What is the rank of a vector? Is it always 1? It can be 0. And we have seen it is of rank 1, except if C dot of T is a 0 vector. And in calculus 2, we have seen that you have a problem if you have, what does it mean? It means you stop somewhere. You fly and you stop somewhere before you start again. You have a 0 derivative. And you have a problem when you have a 0 derivative. Remember, there exists this arc length parametrization. And you have a problem exactly when it was 0. So we are not so far from something we have seen. Of course, it's just a special case, but the Jacobian matrix is this vector. It's usually of rank 1, but it can be of rank 0. For P is, in this case, P is the time now. This is P is the time. In some case, it can have a rank 0 if suddenly there is no speed. Okay. Any question or remark? It's good to see that we are not doing something completely different from what we have already studied. And Jacobian matrices appeared in calculus 2, of course. So in this section 3, we have seen smooth manifolds and function from one manifold to a manifold. This is a capital F, and what means that this function is smooth. And also, if it is smooth, we can define the Jacobian matrix and its rank. The rank will play a role. There is this section 1.4, which I like, but I don't want to spend too much time. If I cannot finish, and I will not be able to finish, I will probably ask you to read a little bit of it so that I can quickly finish it next week. It's called immersion, submersion, and embedding. By the way, sometimes it depends on the author. This E is a I, embedding or embedding. All right. So first, what is an immersion and a submersion? It's very much related to what we have seen. So let M n be smooth manifold. Manifolds. This one is of dimension M, and this one is of dimension N. I use this constant. And consider F from M to N also smooth, in the sense I have just introduced. If rank of F at P is equal to M for any P, so if it is constant and equal to the dimension of this manifold, so if this matrix is in fact invertible, no, it's not, sorry, I said something. If this matrix can still be of M times N matrix, but if you have M independent vectors, we call F immersion. This is just two names. And if the rank of F at any P is the dimension N for any P, F is called a submersion. Now I have an exercise for somebody. submersion. Submersion. Exercise. What's the use? I don't know what is the use of this submersion. I mean, when is it useful? So you can probably just Google it and try to find in which setting it's used. We are going to deal with immersion. By the way, what we have just mentioned here, if there is no point where the velocity vanishes, is an immersion. The manifold M is of dimension 1. Its image, if there is no special point, if the rank is 1, so it's an immersion. So very often we study something of lower dimension inside something of bigger dimension. But in a sense, the other one is the opposite. And I haven't seen yet, but I didn't spend so much time, but I haven't seen when or why is it useful. So if somebody wants to explain when this notion of submersion is useful, it would be a nice report. Okay, you think about it and you write a report. Thank you. But by the way, remark, and we have a good example on the blackboard, even if the rank is constant, it doesn't imply that it's injective. There is no relation. As long as we have no point where the velocity vanishes, this is still an immersion. Remark, immersion is not always injective. And see, this is a good counterexample because it goes 2 times through the same point, but it doesn't really matter. So it's not injective, but we like when it's injective. Okay. So when it's injective is, keep this example, when we have this again from an interval 0, 1, let's say the interval 1, then we have C of t. This trajectory, this would be injective. If F is an injective, now, so I assume that it's injective, is an injective immersion. What you can do something quite natural, but a bit stupid. It's the following thing. We have this interval 0, 1, and this function, C. If I want to be in the general framework, I should call it F, even if in calculus 2, we call it C. I have some open sets here. This is a manifold. So I have the notion of open set. And if it is injective, I can just say, oh, the image of this open set is going to be this open set, right? And I can do this for all open sets. You can take any other open set here and take its image here. So it means you can, on this picture, I can put a topology. I can just take this and because it's bijective, if it is injective, it's bijective on its image. So it's bijective. I can just say I put the topology of the manifold M on its image. It's a bit stupid, but we can do it. So if F is injective immersion, then it is bijective on its image. This is always the case. And what is its image? It's F of M. this is if this is M, now I come back to the general setting. This is M. This picture is f of M. So if f is injective, it's an injective immersion, it's image. It's bijective on its image. And we say we can endo f of M with the topology of f. With the topology of M. We can endo f of M, this image, with the topology of M by f. It goes through. Why it's a little bit stupid? Because N doesn't play any role. It doesn't matter if this bigger space has any property. You don't use it. You just, you use that it's bijective, but you don't use the topology here, right? So the lack of interest of this, however, N does N and its topology do not play. And now let me show you that on an example that it's also interesting to consider the topology of M, the topology of N. So let me just show you an example. It's also in the notes. Consider the real line. This is my initial map, my initial manifold. And I take a picture. In fact, it's misleading to draw this line because it doesn't belong to anything. It's just one line. And now I send it to the following object. But be careful. It means when this goes to infinity, I'm just reaching a certain point. So it means when I move here, but I go more and more slowly. And this point corresponds, the infinity point here is infinity. This is, of course, it's not correct what I'm writing, but the F infinity would be just here. Take, I have an example. Yes, you can take, it's not the same image, but take exponential of minus x. Yeah, okay. When x goes to plus infinity, it just reaches 0. So you need a very long half line to reach 0. It's the same idea. The entire line is copied into this, which converge to this point. Why I'm considering this? Because look, the same picture. If I just consider an open set here, its image by this stupid picture is here, right? But now if I consider we are in R2, this is N. N has some open set, which are balls. So I can consider this ball. This is an open set in R2. And what is the subspace topology for this? It's the intersection of the curve with this ball. So the open set on this picture is going to be this, which doesn't look similar. No, I should be more precise. Let's say this is P, this is f of P. Maybe yeah. If I consider I will come back to this. But if I only consider the topology obtained by the image without thinking about the ambient space, I would do this picture. But now if I keep in mind that this image is in the bigger space, it's natural to use the topology of the bigger space. And then the subspace topology. So the subspace topology of this is this blue part, which is quite different from a neighborhood of the point P. So now we have a difference between the initial topology and the subspace topology obtained by the image of this manifold inside this one. And this is more interesting. So I will start again with this. In fact, it plays this notion of embedding play quite an important role in many things, but it's good to keep this picture in mind. If you use the ambient space, you get more information. I will come back to this. So, but if you have time, just look at the end of this chapter, section 1.4, because I want to finish it in the first part of next week, but I will explain it. There is a difference in just looking at this picture without anything around, or if now you say, oh, we are in a bigger space and we have the subspace topology. Makes a difference. Okay, that's all for today. Is there any questions still? Or online, if you have any question, you can also ask me.